Hello, my name is Andy Podgorski. I'm going to be presenting our paper entitled Counterfall, Value-Based Fault Localization by Modeling and Predicting Counterfactual Outcomes. This is joint work with my PhD student, Yeet Kukuk. First, let me introduce the problem of statistical fault localization, or SFL for short. SFL is a partially automated approach to localizing faults in programs. SFL techniques input execution profiles for a set of program executions, such as code coverage profiles, together with indications of whether each execution succeeded or failed. To this data, the techniques apply statistical measures of association between the failure data and the profile data in order to compute what are called suspiciousness scores. These scores are used to rank program statements so that the ones with the highest ranks are the most likely to be faulty. Most SFL techniques employ code coverage profiles. In the code fragment on the upper left of this slide are small circles representing executions. Green circles represent successful executions that cover the statement to their right. Red circles represent failures. Intuitively, statements with mostly red circles are most suspicious. In essence, SFL techniques attempt to estimate the average causal effect of executing individual statements on the occurrence of failures. In 2010, Ba et al. Showed in an ISTA paper that confounding bias could distort the suspiciousness scores computed by SFL metrics. Confounding is a bias that's due to the presence of a common cause of a treatment variable and an outcome variable in a study. To reduce or eliminate confounding and other forms of bias, researchers employ causal inference techniques. These are based on the idea of counterfactual outcomes. Normally in a study, we get to observe the value of an outcome variable for only one value of the treatment variable. The outcome under the other treatment value is counterfactual, counter to the facts. The fact that we can only observe one of the two counterfactual outcomes is known as the fundamental problem of causal inference. If we knew the counterfactual outcomes under all treatment values, we would compute the individual causal effect under any pair of treatments. Since we don't know all the counterfactual outcomes, we have to estimate average treatment effects. To guide the causal inference process, researchers use causal DAGs, or directed acyclic graphs. These are DAGs in which the vertices represent study variables and the arrows represent causation. In the DAG on the lower right of this slide, the treatment A is a cause of the outcome Y, and C is a common cause of A and Y. C is a confounding variable that lies on a backdoor path from A to Y, which is a path that begins with an arrow into A. A backdoor path creates a flow of association here between A and Y, which distorts the estimated causal effect of A on Y. To eliminate confounding, we can block all backdoor paths, for example, by stratifying our analysis on the value of the confounding variable C. Although most SFL techniques employ coverage profiles, value-based techniques use value profiles, which record the values of program variables. Our technique, CounterFault, is value-based. The treatment variable is the target of an assignment. For example, for the assignment statement in the box, the treatment variable is A. The potential confounders are the variables B and C whose values are used in the statement. One example of a value-based technique is the value replacement technique due to Jeffrey, Gupta, and Gupta. The technique replaces the values used in a statement during one execution with values taken from another execution. The statement receives a high suspiciousness score if the replacement of values tends to change failures into successes. Unfortunately, value replacement is expensive because it requires re-executing a program many times with different value assignments. Counterfault makes use of a program representation called gated single assignment form, or GSA form. Like static single assignment form, or SSA form, each variable is assigned to in only one statement. GSA form is a directly executable extension of SSA form. It uses fee-if, fee-entry, and fee-exit functions to merge data flows carried along different control flow paths. In the example shown here, a fee-if function is added below the if-else statement to merge the assignments to the variable C along the two paths through that statement. Fee functions create shadow data dependencies that can be used to replace control dependencies when forming a causal graph of a program. Our counterfault methods simulate Jeffrey et al.'s value replacement method without re-executing the program many times. It does this by predicting individual counterfactual execution outcomes under a contrast of treatment values. The predictions are made with a machine learning model, in particular a random forest. The model is trained based on treatment, confounder, and outcome values from a sample of executions. The trained model is applied to the same confounder values, but with different treatment values. The average failure causing effect is estimated by averaging over individual counterfactual outcomes. This figure depicts the steps in the counterfault algorithm. First, the program P is transformed into GSA form and instrumented to record value profiles and other information. The transformed program is then run on a set of inputs to collect value profiles. They're used together with pass-fail execution outcomes to train a random forest model for each assignment statement. The model for a statement is used to predict counterfactual outcomes for pairs of representative treatment values. An average failure causing effect estimate is computed for each pair by averaging over counterfactual outcomes and taking differences. Finally, a suspiciousness score is computed as the maximum average failure causing effect estimate over all pairs of contrasting treatment values. We conducted an empirical evaluation of counterfault in which we compared it to 7 other techniques. As subject programs, we used programs from the Defects4j benchmark and the Apache math library. From Defects4j, we selected only versions with real faults involving assignment statements. For the Java numerical programs, we injected faults into the assignment statements. This figure presents our results for the Java numerical programs with a 50% failure rate. Each bar represents the percent cost reduction achieved by counterfault over a competing technique. The bars which are below the 0% line are cases in which counterfault did worse than a competing technique. We compared counterfault to the value-based techniques NumFL-QRM, NumFL-DLRM, and ESP, and to the coverage-based techniques OKI, the F1 measure, CLOSGEN, and DSTAR. As the figure indicates, counterfault performs best overall. This figure shows the results for the Defects4j programs. As you can see, Counterfault performed better on average than all of the competing techniques for all subject programs. That concludes my short presentation, and I'd be happy to answer your questions.